Hey everyone, so today with lesson 12, we're going to just dive into the inverse cosine and sine functions, okay? So right here at the beginning, what they're doing is they're graphing sine and cosine. But as you can see, if you switch x and y, you graph it, all of a sudden it's no longer a function, okay? Because the idea is if we kept going up like this, right, it would not pass that vertical line test. So what we have to do is restrict the domain for the inverse. So the idea that I want to show you is that for sine, you can see that we would have a function, if we switched our x and y's, between negative pi over 2 and pi over 2. We wouldn't do 0 to pi or 0 to 2 pi because, again, it would not pass that vertical line test once we switch our x and y's. So our domain restriction for sine is negative pi over 2, pi over 2. So that means we're just looking at the first and fourth quadrant. For cosine, though, if you see where we have a nice layout here, is between 0 and pi. If we did negative pi over 2 to pi over 2, like we would have done for sine, you would see too that, hey, we switch x and y, and we no longer pass that vertical line test. So this is the idea behind these two. And cosine, of course, would be the first and second quadrant. So there are two ways that you can see when they want the inverse, and we have the sine to the negative 1 of x, or arc sine. Same thing with cosine. Either one of these says inverse. So remember when we were taking trig functions, we were saying a trig function of a theta equals an amount, a number, okay, or a coordinate, right? Y value. But if we go backwards, what we're saying is what theta makes that Y value, okay? So when we think of this, we need to think of our coordinates on the outside of our unit circle and what theta works. And don't forget those domain restrictions. So what I do when it comes to remembering those domain restrictions, I automatically sketch out my unit circle of the quadrants that I'm able to use. So for cosine, I'm able to use the first and second quadrant. And if I look, cosine on the second quadrant is negative. Cosine on the first quadrant is positive. And we're at a positive 1/2. And by now you know your unit circle really well, which here's the coordinate of 1/2 square root of 3 over 2. And what theta is that? That is at theta pi over 3. Okay, arc sine. Again, we're looking at the first and fourth quadrant. We're looking at sine being positive. If we look, it's positive in the first quadrant, but not the fourth. So we're looking right here, which is the coordinate square root of 2 over 2, comma, square root of 2 over 2. So the theta that makes this true is pi fourths. All right, let's sketch that unit circle again. Now, don't forget we are doing a negative cosine, which means it's going to be in that second quadrant there. Square root of 2 over 2, that's negative, comma, square root of 2 over 2. So think of what theta that is. That theta is 3 pi over 4. All right, and sine. This is the one to be tricky on. Because, okay, right away we see it's a negative 1, right, guys? So it's in the fourth quadrant. So we're down here. We're looking at that coordinate of square root of 3 over 2, negative 1/2. Now, looking at that theta, this is where you got to be careful. Because we're tempted, right? We're tempted to say 11 pi over 6. But 11 pi over 6 is actually this full arc, or this full radian right here. But we can't go in here, otherwise we don't have a function. So actually, and I'm going to erase this so I don't mess myself up later. we have to go backwards. We have to actually start at our 0 radians and then go backwards. So backwards means negative, and we're going back a negative pi 6. So when we are in the 4th quadrant, guys, it's going to be a negative radian. Now, it would be nice if we stopped there and we'd be done and we could practice, but we got a few other ones that can complicate things. Now, with these, sometimes it is tempting to just cross them out. Don't do that. Do the inside, outside, okay? So first of all, cosine pi over 6 is cosine, well, cosine pi over 6 is square root of 3 over 2. So I'm going to plug that in. And now I go back to what I did on that first page there. I think of my unit circle. Cosine is 1st and 2nd quadrant. This is in the 1st quadrant. So it is pi over 6. So yes, in this case, it's like they canceled out because they happen to be in the same quadrant. But this doesn't always help. An example or work. And this example here shows us. So we have cosine -1. Now, cosine 11 pi over 6 is in the 4th quadrant. It is square root of 3 over 2, still the same as an e there. But now when we think of the inverse, where is the square root of 3 over 2? Because it can only be in the 1st or 2nd quadrant. It's in the 1st quadrant. It is at pi over 6. So see how you can't just cross them out. It's just better to get in the habit of going inside, outside, and it works just fine. Okay, here's one that 3/5, well, that's not really a perfect answer on our unit circle. But remember, when we're going backwards, we're trying to find out what theta matches this. So what I'm going to do is say to myself, draw this out, well, the 1st and 2nd quadrant, right? And I know since cosine is negative, it's going to be in the 2nd quadrant there. It's going to be some sort of theta. Okay, so let me look at this as cosine -1 of -3/5 is some theta, which means if I solve this equation right here to get rid of an inverse cosine, I take the cosine of both sides, and I get -3/5 equals theta. So our answer, or cosine theta, sorry. So when I take the cosine of our theta, I still get -3/5. Let's do it a little bit different, see how this works, okay? So first of all, I want you to see that this is still in quadrant 2. Quadrant 2, which for sine, we have to keep in mind, oh, this is an arc sine, so it's okay to be in quadrant 2. It's only when you do the inverse that you need to restrict that domain. So again, I'm going to draw this out so you guys can see it. I know I'm in quadrant 2 at some theta. So if you think about it, if this coordinate here is -3, 5, we need to figure out what the sine coordinate is. All right, well, cosine is adjacent over hypotenuse. We can use the Pythagorean theorem to find the other side, which in this case is 4. Hopefully you guys know that right triangle by heart. So that means sine is opposite, or y over r. You can go back to our x, y's, and r's. So that means in this case, sine of our theta, even though we don't know the exact theta, is still 5/4. So we're able to do those. All right, so we're doing 2 more problems restricting the domain, or it says, rewrite the following as algebraic expressions of x and state the domain on which the equivalence is valid. Okay, so first of all, if we look our cosine, right? All right, so if I think of this, and I'm going to think of a theta right here, where cosine is x. Well, think of this. X is x over 1. So that means it's going to be x over 1. Do the Pythagorean theorem. If you want, I can show you. X squared plus, or y squared equals 1. Solve for y, because that's what we're trying to solve for. So I get y equals the square root of negative x over x. Did I go too fast on that? Negative 1 square root. Sorry guys, I'm going too fast for my own good. All right, negative y. Oh, sorry. There we go. I'm going too fast. Okay, so we get the square root of 1 minus x squared. Okay, so in the future, we're going to think of this as positive, negative, but this is a positive x. We're going to think of it as a positive x here. So if y is the square root of 1 minus x, and I'll put that in right here. Right, which actually that coordinate would be square root of 1 minus x over 1. Okay, now we're finding tangent of that theta. So tangent of the theta, which is y over x, comes out to be the square root of 1 minus x over x. Now, since the domain is restricted with cosine, remember with cosine in arc cosine, we're only going from negative 1 to 1. So there's our first restriction. Remember when we, sorry, I didn't know I didn't have that up there. We have our restriction with arc cosine, the inside. But now let's talk about what happened with our tangent. Because right now here is our restriction based on arc cosine. But if you look at the tangent right now, what else can't it be? What can't happen in the denominator? Well, it can't be 0. So you have to look at both parts to where your domain is restricted. So that means we're going from negative 1 to 0 and 0 to 1. And we are done. All right, let's check our other one here. So we have 2 arc sine of x. Okay, well, let's keep in mind that arc sine of x is some theta. So we have arc sine x equals theta. So let's think of this. If I were to solve for x here, I would get x equals, actually, let's keep it as arc sine. You know why? Because that too. So arc sine x equals theta. So if I rewrite this, I get cosine 2 theta. Now what happens here is that we have to use our double angle theorems. Hopefully by now you have memorized them. Remember, there are 3 options we have. Now, because we are dealing with, when I solve for this, like I was about to, sine of theta equals x, I want to have sine in my double angle here. So I'm going to use the 1 minus 2 sine squared theta. Now, why did I use that? Because if I manipulate this arc sine x of theta, we get x equals theta, which now I can replace sine theta in here with x, leaving us with 1 minus 2x squared. So we're done because we got to our algebraic, because cosine of double angle would be that. And then if I look at my restrictions, well, arc sine, again, the domain goes from -1 to 1. And there's no extra things that we need to think of that don't work. And we're good. All right, let's try some of those for practice.